Hello, welcome to my channel QD8. Today we are going to talk about Stern-Gerlach experiments and how they reveal the existence of electron spin and how the properties of electron spin are really weird. Let's get started. So here is the outline. We'll first talk about the Stern and Gerlach experiments, which reveal the existence of electron spin. Then we'll talk about sequential Stern-Gerlach experiments where we connect multiple Stern-Gerlach devices and see how it leads to weird quantum behavior. And to drive home that point, we'll do a similar experiment with cats and show how weird it is, how weird this whole property of quantum spin is. Let's get to the experiment. So in 1922, Stern and Gerlach did this experiment where they heated up silver atoms in this furnace and sent them through the slits into this magnetic field pointing in this direction. And as these silver atoms passed through these bar magnets, they got deflected. And according to the classical physics, the classical mechanics and electrodynamics that was known by then, the silver atoms were supposed to hit along a line on the screen here and they would get smeared out. But what was found was that there were only two regions where the silver atoms hit the screen, and that was really weird and unexplained by classical physics. So let's see an animation about that. Here is an animation from Wikipedia. So first we have classical particles which are modeled as magnets, little tiny magnets, and I'll explain later why. And when they're sent through this magnetic field, they get deflected by these magnets and they hit the screen at random orientations and they get smeared out as shown in this animation below. But now if we do the same experiment with quantum particles like electrons, what we see is completely different. The electrons, they get deflected, but they just get deflected only in two particular locations, either up or down, as we see in this animation below. And this could not be explained by the classical physics, and this is a completely quantum property. And we'll explain more about this in the coming video series. And now going back to our presentation. So what this experiment revealed was the existence of a new quantum property, and that's called intrinsic angular momentum. It's also called as spin angular momentum. And other quantum particles other than electrons also have this, and they're called spin 1/2 particles. And this experiment showed that the spatial orientation of the spin angular momentum is quantized. We'll unpack this in the later videos. So at that time in 1922, what was known classically, the most advanced model was the Bohr-Sommerfeld model of the hydrogen atom, where the electron can travel inside the nucleus. It would orbit the nucleus only in fixed orbits, and the orbital angular momentum of the electron was fixed, and Bohr kind of postulated this, it's arbitrarily fixed. And Stern did not like this whole theory, and he wanted to come up with an experiment and show that this whole thing is wrong. So if from classical physics, if something is either revolving around an axis or rotating around an axis by itself, then it has angular momentum. This is the orbital angular momentum, and this is the spin angular momentum. And on top of this, if that particular particle has charge, then it acts like a tiny magnet, also called magnetic dipole. It acts like a little magnet, and the strength of that magnet is called magnetic moment, and that magnetic moment is in the direction of the angular momentum. So the magnetic moment is k times, it's just a scalar, where k is a scalar, times the angular momentum vector. So what happens classically is that when this particular tiny magnet is present inside a magnetic field, so the force it experiences, among other things, it is proportional to cos theta of the angle between the magnetic field B here and this particular tiny magnet. So when these silver atoms are coming out of this oven, um, it turns out that they behave like tiny magnets, uh, and they can come out at random orientation. So the theta is random. So you just see a spread out pattern here. What we have is these tiny silver atoms, which can be treated as tiny magnets, and when they go through this magnetic field, they get spread out here. And but uh, but what actually happens is when these silver atoms go through this magnetic field, they're getting deflected only into two particular orientations. And this is this strange, classically non-describable two-valuedness, which the famous scientist Wolfgang Pauli described it as. So we're going to unpack more about this. So here is a beautiful article in Physics Today, and it talks about the history of the Stern-Gerlach experiment. And this is the photograph which Stern sent to Bohr, and this is the photograph without the magnetic field, and this is with the magnetic field, and you see these two distinct regions where these atoms are getting deposited. So the magnetic field is along this direction, and Stern congratulated Bohr, saying that it's a confirmation of their theory, but at that time they didn't really know what they found, and what they thought that this experiment proved the existence of orbital angular momentum and that it is quantized. But it turns out that is not the case. For silver atoms, in this case there is zero orbital angular momentum, and scientists thought about this. Where is this property coming from? And the same experiment can be done for hydrogen atoms, and it was shown later in 1927, the similar pattern here for hydrogen atoms. And this is a fantastic experiment of this. There's a fantastic Stern-Gerlach experiment done using cesium atoms at MIT, and you can see this video. It's really fantastic. So scientists thought about this in 1920s. After this experiment, scientists thought about what is happening here, and they also looked at other experimental evidence from hydrogen spectra. And two scientists, graduate students, Uhlenbeck and Goudsmit, they came up with the weird proposal that this property, whatever you're seeing, is because of the electron spin. They hypothesized that maybe the electron is kind of spinning around its own axis, and because it's a charged particle, that spin is causing a magnetic field, and that magnetic field, when it interacts the magnetic field of the Stern-Gerlach device, it is showing this strange quantum behavior. But Ehrenfest was the PhD advisor for Uhlenbeck and Goudsmit, and after they submitted this paper, he had this calculations checked by Lorentz. And if you use classical mechanics, what happens is that is nonsense, because in order for the electron to show this behavior, it needs to rotate at 10 times the speed of, it needs to go around the atom at 10 times the speed of light, and it doesn't add up. It's nonsense. So what physicists since then think about electron spin, when they think about electron spin, they consider it as an abstract property or intrinsic property. They don't know why electrons have spin. They just call it an abstract property. So the electron, all the physics textbooks you see, they say electron is not spinning, but it behaves as if it was spinning. So we need to be careful. So there's nothing really spinning. So if there's nothing really spinning, where does quantum spin come from? So even now, this is a mystery, and there's a fantastic article in Scientific American about this. And this physicist from Caltech, he came up with a new model, and he thinks he can explain where this spin is coming from. But I have only done a course on quantum physics and quantum computing in grad school, and I have not done the relativistic quantum mechanics and the quantum field theory and other deeper theories. So I couldn't really understand anything about this, but this is a nice resource for you if you want to check this out. So let's go to our Stern-Gerlach setup, and we'll do some sequential Stern-Gerlach experiments. So by sequential Stern-Gerlach experiments is we stack together multiple Stern-Gerlach devices and see what happens. So here's the experiment 1. This is a simple experiment. So what we are doing is we are aligning the magnetic field in the z direction here. We are aligning the magnetic field in the z direction, and then the particles get deflected, spin up or spin down along the z direction, and then we are passing the spin up particles which were detected here. We pass them through another Stern-Gerlach device which also has its magnetic field oriented along the z direction, and see what happens. So what will happen is, since we have filtered out all this spin down particles, what we expect to see is just spin up particles, right? That sounds plausible, nothing surprising here. So if we abstract this away, this device away, we have Stern-Gerlach device with magnetic field in the z direction, and say we send 200,000 electrons or atoms into the Stern-Gerlach device. We see about half of them, 50%, will be spin up and 50% will be spin down, and we block the spin down particles, and then we let the spin up particles pass through. And when we do some measurements, we see that exactly, say 100,000 particles will come into this device, and all 100,000 particles, when we measure them, we see that they have spin up. Nothing surprising here, right? And it looks like it's kind of like a classical setup here, but the only thing surprising aspect is that spatial quantization. You only have spin up or spin down. And you can do the same experiment in the x-axis, where we pass through this Stern-Gerlach device, two Stern-Gerlach devices, one magnetic field in the x-axis, other magnetic field in the x-axis, and you do the same thing, you get the same result, where you have the spin up along x-axis and spin down along x-axis, and you do the same thing along y-axis, you get the same result. So the spin angular momentum is actually quantized in all three directions, in x, y, z. You measure it in x, y, z directions, it's quantized, it's spin up, spin down, that's all you get. And this is the surprising aspect, and it cannot be described classically. So now we do a second experiment. What we do is we connect one Stern-Gerlach device with magnetic field in the z direction. So we are doing a measurement along the z-axis, a measurement of the spin along the z-axis. So, and then we connect it to a device where we measure the spin along x-axis. So if we send 200,000 or 400,000 atoms into the first device, and we are blocking the spin down, so only 200,000 of them pass through, and then and all of these have spin up, all of these particles have spin up, and when they pass the spin, when we measure the spin along the x-axis, what we find is that about 100k of them have spin up along x-axis, and 100k have spin down along the negative x-axis. So what this shows is that even if you're certain, so in this we are certain that we have spin up particles, but when we measure along x-axis, there's uncertainty. Half of them are spin up and half of them are spin down, and you can do the same thing, because right now we're doing this spin along z and spin along x-axis. You can do zy and then xy, yx, and all combinations. You do that, you get the same behavior, same weird behavior, where if you know the spin along one particular axis, say spin along the z direction here, and there's complete uncertainty along the x direction, it's either spin up or spin down along x-axis. A more appropriate way to spin left or spin right, but along x-axis, and there's this 100% uncertainty along the other axis, and this is the weird uncertainty which we see only in this quantum mechanics, and this kind of uncertainty is not seen in classical mechanics. And now we'll do another weird experiment. So what happens, we now have three devices. What we do is we send the atoms through the Stern-Gerlach device, which measures the spin along the z-axis, and then block the spin down particles, and then we send them through the Stern-Gerlach device which measures the spin along x-axis, and then we block the particles which point along the negative x-axis, only let them pass, only the spin right particles pass through, and see what happens. So let's say we have 400,000 silver atoms, and about 200k will have spin up. We pass them to the Stern-Gerlach devices, and as seen in the previous experiment, half of them will be like spin left and spin right. So we get 100k here, 100k, about 100k in spin right, and then we pass them through this another Stern-Gerlach device, which is measuring the spin along the z-axis. So we know that all these particles which come through this device, right, all of them have spin up along the z-axis, right? That is what we have observed. So intuitively, by classical logic, if you were to think what is going to happen, you might think that now we'll just see all the 100k which pass through this device, all the 100k silver atoms, they will all have spin up along z-axis. But what happens is completely counterintuitive. You have about half of them, 50k along the spin up along the z-axis, and another 50k along spin down along the z-axis. So this is completely counterintuitive, right? If we have blocked out all these particles with spin down along z-axis, right? We are only letting spin up particles along the z-axis, and we make a measurement along the x-axis, and we pass through only this spin right particles, and then surprisingly we're getting back the spin down particles along z-axis, and we thought we blocked all of them. That is really, really weird. This is the weird aspect of quantum mechanics. And if you think, to drive home this point, if you think this is not surprising, let's do a simple experiment. Let's do the same experiment with cats or with classical particles and see why this is really surprising. So now we have set up where into a Stern-Gerlach device we'll send some cats. These cats have two orthogonal features, say z or x. The z feature is all these cats, they're either gentlemen which have a bow and a mustache, or they have a bow and a necklace. Gentle ladies have a bow and necklace, and all the gentleman cats have a mustache and a bell, right? That is one feature. And the other feature is all these cats come in only two colors. They're either green or they're either blue. That's it. So right, these are classical analogs of spin. So let's do this experiment with cats. So what we'll do is initially we'll line up all these cats and we will send them through the Stern-Gerlach device. So now the first Stern-Gerlach device, what it'll do is it'll just select the cats based on their say gender. So all the cats, lady cats with a bow and necklace, think of them as spin up along the z direction, and all the gentleman cats can think of them as spin down, right? So we filter out. We do not let any of these gentleman cats pass through this Stern-Gerlach device. They are blocked. They're filtered out. We only let the gentle lady cats to pass through, right? When they pass through this other device, where we will only check for color in this. So that is like this, the spin left or spin right? So let's say half of them, you send in these. So out of the total, say you send in like 400,000 cats. To about 200,000 of them are like gentle women cats, and 200k gentleman cats are blocked, and we send them through this other Stern-Gerlach X device. So we see that about 100k, about half of them are blue and about half of them are green, right? Nothing surprising here. But now we send them back, all these gentle lady cats, right, which came like spin right in the x-axis, which we measured. We will send them to this other Stern-Gerlach device, which only checks for gender. Then what we see is that not only do we see half of them, like 50k of them they have these bows and necklaces, and the remaining half of them, they have a mustache and a bell, And this is completely counterintuitive, right? We have blocked all of these gentleman cats, and how did they show up here, right? This is the weirdness of this quantum logic, and this is completely mind-blowing, right? So now I think now you can appreciate why this whole spin business is really weird, and how scientists have come up with a mathematical model to describe this kind of weird quantum behavior, right? And if you use classical logic, and this cannot be explained using classical logic. So in order to describe this behavior, and that is the triumph of quantum theory, is that they came up with a mathematical model to describe this kind of weird behavior. Even like simple systems, right? Spins, they display this weird quantum behavior, and in order to describe this, they came up with a mathematical theory. All these great scientists like Heisenberg, Schrödinger, and Paul Dirac, they came up with theory. And all you need to, in order to describe this kind of weirdness, all you need is just complex numbers and two-dimensional vectors and matrices. That's all you need to describe all this complex behavior. And we'll explore further in the next set of videos why you need complex numbers and why you need complex vectors to describe this kind of behavior. And for now, we have enough quantum weirdness to deal with. So thank you very much for watching my video. Have a great day. Bye.